wrap up chapter 9. And again, I know this is a difficult chapter. It's difficult in class. I can only imagine how difficult it is in this situation. But it is a really important chapter, especially if you're going to take Integrated 3. So hopefully those of you guys are going to take Integrated 3 really try to stick in there and figure this out. Anyways, the last one, 941, inverse functions. I think this is pretty cool. It's essentially undoing something and making your inputs your outputs and your outputs your inputs, which is kind of interesting the way it works out. So have you ever noticed that it can be easy to do some things forwards, like recite your ABCs or say the Pledge of Allegiance, but it would be difficult to do the same those same things backwards. Today you will write the equations of inverse functions, which is the same as working backwards through the function. As you work today, keep these questions in mind. How can we undo it? And how can we justify each step? I always get questions in class like, why would we do this? Which is a legitimate question, but think about it. Let's say we were, you made $15 an hour and you made $12 just for showing up. Well, let's say you were only working because you wanted to save $800 to buy a stereo system. Well, the thought would be, if you do the inverse function, you can just work backwards to figure out exactly how many hours you need to do, as opposed to like guessing and checking or doing it the back way. So essentially your y becomes your x and your x becomes your y. That's really the thing. So we always solve for outputs. If we do the inverse function, we solve for inputs. And I mean, there's a lot of scenarios that can be useful. Anytime you know the output, but you don't know the input is an example of that. So I don't want to spend a lot of time on this video justifying its existence. A function machine is pictured at right. When 3 is put into the function machine, it pops out a 13. And when 4 is put in, it gets a 16. And when -3 gets put in, it gets a -5. So explain in words and write an algebraic equation for what the machine is doing. Well, it looks like my slope is 3, right? So y equals 3x. And then when I plug in 3, I get 13. So it looks like if I plug in, it looks like I'm adding 4, right? So 3 times 3 is 9, plus 4 is 13. 4 times 3 is 12, plus 4 is 16. -3 times 9 is -9, plus 4 is -5. So it looks like this is my equation. So we will say f of x is equal to 3x plus 4. That's my function. Ambrose really wants to work for Functions of America. He is applying for a job in the recycling department. Oh, geez. In this department, outputs are put into inverse function machines. The inverse function is written f of 1 x, f to the -1 x, undoes an output and recreates the original input so that it can be recycled and used again. For example, when 13 is put in, now he's changing this, right? So this is f of x. This is f of x. He wants to make something that is the inverse of that, so that when he puts in a 13, it spits out a 3, and when he puts in a 16, it spits out a 4. If he spits in a -5, it spits out a -3. So you can see the x and y's change. So the question is, what would be this function? How would he write that? And how would we do it? And it's really a pretty simple thing. It all is based on the order of operations. Please excuse my dear Aunt Sally, right? Parentheses first, exponent second, multiplication, division third, addition, subtraction last. So what we would do is we would look at this equation and say, well, the first thing, if I knew what x was, the first thing I would do is multiply by 3, right? And the second thing I would do is add 4. So if I'm going to do the inverse, what I need to do is start from the bottom and work my way back up. What's the opposite of adding 4? Subtracting 4. What's the opposite of multiplying by 3? It's dividing 3. So that becomes my inverse function. It's really that simple. I'm going to go here and I'm going to write in a function that says x minus 4, and then I'm going to divide that whole thing by 3. Because that's the opposite of what's happening here. Here I'm multiplying by 3, then adding 4. So here I'm doing the opposite. Instead of last I'm adding 4. To undo that, I'm going to subtract 4. Then I'm working my way back up. Instead of multiplying by 3, I'm going to divide by 3. So it works backwards. If you plug 13 in, 13 minus 4 is 9. 9 divided by 3 is 3. If I plug 16 in, 16 minus 4 is 12. 12 divided by 3 is 4. If I plug negative 5 in, negative 5 minus 4 is negative 9. Negative 9 divided by 3 is negative 3. So that becomes my inverse function right there in this particular example. So write an equation for the inverse function. F of negative 1 is x equal x minus 4 over 3. I will say something else. Actually, I guess it doesn't matter if we put the parentheses there or not. This negative 1 has no mathematical value at all. It's just simply a way of saying it's the inverse. So if I say f of x or g of x, I'm naming equations or functions that come next. If I say f of negative 1 x or g of negative 1 x, I'm just saying that this is the inverse to this function. Whatever this function is, this is the opposite. Whatever this function is, this is the opposite. That's how that works as far as the inverse goes. So again, it really is based on the order of operations and doing them backwards. So let's go ahead and take a look here. Kimberly is also applying for a job with the recycling department. Before the interview, she's given the function machine g of x and told that here's what g of x does. G of x multiplies x by 5, then it subtracts 8, then it divides by 2. So that's my function for g of x. Well, what do I get if I plug in 3? Well, I get 15 minus 8 is 7. 7 divided by 2 is 3.5. So if I plug in g of 3, right, if I plug 3 in for x, I get out 3.5. I hope you guys remember this function notation from integrated 1 a little bit. I'm hesitant to go into this too much right now just because we're trying to teach other things. But function notation, again, is f of x equals 3x plus 2, for example. F of x is the y, x is the x. So when I say like f of 2, I'm saying go into that equation and plug in 2 for x. I hope that rings a bell. Again, I do not want to get too far down this rabbit hole. So what am I going to get for my inverse function? Well, again, I'm going to work backwards. What's the opposite of dividing by 2? The first thing I'm going to do is I'm going to multiply by 2. Then what's the opposite of subtracting 8? I'm going to add 8. Then what's the opposite of multiplying by 5? I'll divide by 5. So this is going to be what I do. So my inverse function for g is going to be, I'm going to multiply x by 2, then I'm going to add 8 to it, and then I'm going to divide the whole thing by 5. And if I plug 3.5 in, I expect to get 3 out, because remember, those x's and y's trade spots. So if I plug 3.5 in, 2 times 3.5 is 7, plus 8 is 15. 15 divided by 5 is 3. So there we go. The input became the output became the input. Moving along here, n of x. So n of x, the first thing I would do is multiply by 4. The second thing I would do is I would subtract 12. So I'm going to do the opposite of that. And the first thing I'm going to do is add 12. The second thing I'm going to do is divide by 4, right? So I'm going to take this and I'm going to say my inverse function, maybe I should write it over here to give myself some room. My inverse function of n is going to be first to add 12 and second to divide by 4. That's going to be my inverse function. How do I check this? Well, let's just pick a number. Let's plug 5 in. If I plug 5 in to this function, I get 20 minus 12 is 8. So that means if I plug 8 into this function, I better get 5 out. 8 plus 12 is 20, divided by 4 is 5, so it works. What if I plug 2 in? 2 times 4 is 8, minus 12, I get minus 4. So if I go to the inverse function and plug negative 4 in, I should get 2 out. So negative 4 plus 8, negative 4 plus 12 is 8. 8 divided by 4 is 2. So that works fine. So you can see that this is the inverse function. Now, let's go ahead and write the inverse function for j of x. But again, before we do that, we first need to see what's happening in j of x. So the first thing I'm doing is I'm subtracting 7. The second thing I'm doing is dividing by 10. So that means I need to do the opposite. The first thing I'll do is multiply by 10. The second thing I'll do is add 7. So my inverse function here for j needs to be, oh no, are you kidding me right now? Okay, good. That was not going to make me happy at all. Okay, so the first thing I'm going to do is multiply by 10. So I'm going to get 10x, and then I'll add 7. So that's my inverse function. And again, let's double check this with a couple numbers. Let's plug in 27 here and 37. I'm plugging in weird numbers because it'll work out better. So if I plug 27 in here, 27 minus 7 is 20, divided by 10 is 2. If I plug in 37, 37 minus 7 is 30, divided by 10 is 3. That means if I go to my inverse function and plug in 2, I should get 27. 27. If I plug in 3, I should get 37. 37. So it worked out fine. What I've done, the last thing I want to show you, again, I hope it makes sense how you get it. You just do the opposite. The input becomes the output, but I wanted to show you something I think is kind of neat with these in Desmos. You'll see here I have the equation y equals x. And essentially what I'm saying is the y and the x are equal to each other. Just like in the inverse functions, the x and the y's flip spots. So the first problem that we did, this is problem 125. Here's the two equations that we came up with. And you'll notice that they reflect across y equals x, which makes a lot of sense. Because this point right here is 4, 0. This point right here is 0, 4. The x and the y switch spots. This point right here is 10, 2. This point right here is 2, 10. Again, it makes sense because the x and the y switch spots. And what you'll see is you'll see that symmetry for all these. So here is problem 126. Again, you see that they are reflect across y equals x. And again, this is 0.64. Y should have a point at 4.6. That is the reflection of that. Here you have problem 127a. So 127a, they reflect across y equals x. And as is always the case, here's a point 2, negative 4. So if I go to negative 4, 2, I should have a point because, again, they reflect. And finally, you will see this is 127b. Same thing, they reflect across y equals x. There's 0.70, there's 0.07. Just because the x and the y take each other's spots in an inverse function. So that is that for it. We are done with chapter 9. Yippee, this chapter is a bear. Have a good one. Reach out if you have questions.